You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
So if you've heard anything about quantum mechanics, you've probably heard that it's weird, like capital W weird. So today we're going to unpack that weirdness and take a deep dive into the features of quantum mechanics that are the most surprising and make the least intuitive sense. So in our tour through quantum weirdness, our first stop is going to be at the very nature of light itself, and we're going to learn about something called the wave-particle duality of light. If you heard our previous episode about the discovery of quantum mechanics, this may sound familiar, but the story really started at a particularly influential experiment called the double slit experiment.
So in its earliest form, the double slit experiment was really just a way of showing that light is made up of a wave. It's an experiment where you take some light of one wavelength or as much as one wavelength as you can, and you shine it through a sheet with two slits in it. So essentially you have two different sources of this light coming out of that sheet. And then that light shines onto a second sheet where those two waves combine, and where the two waves have a common peak, the light you see gets brightened. It adds up together. And where a peak of the wave hits the trough of the other wave, those waves cancel with each other, leaving a dark spot. So the result of this experiment is that you get a pattern of bright, dark, bright, dark, bright, dark all the way down the sheet. And that demonstrates that light behaves like a wave, not like just some sort of simple particle-like object.
And that's because if it was a particle, it would act completely differently. Imagine throwing baseballs through two slits.
You'd get a bunch of baseballs in front of one of the slits and a bunch of baseballs in front of the other slits, but no interference pattern. What it comes down to is there's no way to take two baseballs and put them together and get less than two baseballs. But I can take two waves, put them together, and have the positive of the peak of one wave cancel against the trough of another wave, leaving you with nothing at all. So waves have this fundamentally different character in that they can undergo this interference that we're talking about.
Okay, so by shining light through the double slit experiment, it was pretty much established that light acts like a wave.
Well, then we get to the 20th century, and it's 1905, and Einstein's Nobel Prize-winning paper on an experiment called the Photoelectric Effect gets published. So the photoelectric effect was an experiment no one understood, and Einstein didn't conduct the experiment. He just figured out what it meant. But this experiment showed that when you shine light on a metal plate hooked up to a circuit, you could generate current around that circuit, but it only worked if the frequency of the light was high. And no one knew what this meant before Einstein, but Einstein figured it out. And basically what he said is that light comes in fundamental groups, things he called quanta. Today we'd call those quanta photons or particles of light. And the amount of energy carried by those individual pieces of light is proportional to their frequency. So high frequency light carries with it a lot of energy, and low frequency light carries a lot less energy. So those high frequency photons of light could generate current and by breaking off electrons from that metal, whereas the low frequency light just couldn't do that. It's kind of like the analogy I like to use is if you're driving down a country road and your windshield keeps hitting mosquitoes, you can hit mosquitoes for, every day for a year and your windshield won't break. But if you took all those mosquitoes together and put them into a 10-pound ball and dropped them on your windshield, it would just shatter instantly. Einstein,
that's terrifying.
The giant ball of dense mosquito matter. But yeah, Einstein basically showed that, you can't make this current happen by a bunch of low energy light. You need big pieces of energetic or high frequency light to do that job. So light is not only a wave, it is a wave, but it's also a particle at the same time.
So just to linger on this whole idea that light is both a wave and a particle really is hard to grasp.
You shouldn't think of that wave as being made up of photons but rather that photon is itself a wave. Which, by the way, for the first time you're hearing that, that makes sense. It means you're not thinking about it right, because it's super weird, super counterintuitive. If it makes sense to you immediately, you're not getting it. It shouldn't make sense the first time you hear about it, or maybe the 45th time you hear about it.
Yeah, I've heard about it this many times and it still doesn't really make sense, because I'm like, I guess the first image you think of is literally just like a little ball with like a wave trapped inside.
Yeah,
that's a photon, but that's
that is not what a photon is. No. It's the smallest bit of light you can have, and it's a wave also.
So after this wave-particle duality of light was established, a physicist named Niels Bohr suggested that maybe the same would be true about electrons in an atom.
And he imagined a picture where there's a big dense nucleus, like a proton or whatever, positively charged nucleus in the middle of the atom. And then instead of like simple like planetary orbits around that center, there are waves of electrons going around that center nucleus. And it turns out you could explain a lot about the behavior of atoms this way. You could explain why there was kind of a minimum energy state for those electrons. The electrons in classical pre-quantum physics would just in-spiral rapidly into the nucleus, crashing into the nucleus in a very small fraction of time. Any charged particle would do that. So that's not the answer. We know atoms are reasonably stable, and in classical physics as they shouldn't be. We can also use Niels Bohr's model to explain why different kinds of chemical elements give off very specific patterns of light. By this point, it had measured that different, like you take hydrogen and heat it to a certain temperature and study the light from it, you will see specific frequencies or wavelengths of light emitted very brightly. No one had a clue prior to Bohr's model as to why that might be, but he could explain it. Basically, you go from something like the second most least energetic state to the first most energetic state, instantaneously releasing a very specific energy of light or frequency of light in that process. So you could explain these sorts of observed features, at least approximately. The models got better later. Now we can explain this stuff very accurately, but back then it was still pretty crude. But to do that, you had to think that electrons aren't just particles, which they are, but also behave like waves. They could interfere with other electron waves, or even their own electron wave.
And one way you could empirically test this wave nature of the electron is by shining it through that same double slit experiment that we talked about before.
It's a pretty challenging experiment to do, but people have done it now, where you actually, instead of shining light through the double slit, you shine electrons. And quantum mechanics was vindicated. Those electrons produce the same sort of interference patterns that you see with light. I think it is just it's fair to say that it is just an empirical fact that electrons behave like waves.
And it's not just electrons. Every particle is both a wave and a particle.
Yeah, quarks, neutrinos, W bosons, Higgs bosons, muons, taus, all of it. All of them behave both like waves while also being particles. So it's the same sort of particle wave duality that Einstein was wrestling with in 1905. That just seems to be a facet of, as far as we know, everything in nature.
So when does a particle behave like a wave, and when does it behave like a particle? Like, can you control that?
It really depends how you choose to think about it. I'll tell you how I choose to think about it, and kind of historically how people wrestled with it. So if you take a course in quantum mechanics, which of course you have, you learn to manipulate something called the Schrödinger equation quite a bit. And this is a wave equation. This describes how something called the wave function of an electron, or whatever else really, but let's say an electron, how the shape of that wave function evolves, or what the different possibilities for the shape of the wave function can be in different kind of physical circumstances. So from a Schrödinger's equation perspective, electrons are just waves. You treat them the same way that pre-quantum physicists would treat light. But Here's really the trick, is when you do a measurement and you look at, I don't know, let's say we do a double slit experiment, but we only shine one electron through it at a time. And then we look at where that electron hits the screen at the far side. Well, you don't get a probability distribution when you do this. You get one electron in one place. So when you do the measurement, you don't really see a wave. You see something that you would call a particle. So what it looks like, to casual glance, and what I think most, physics students probably get taught, is that you have a situation where things in quantum mechanics behave like waves until you do some sort of measurement, and then they take on a concrete and specific value of whatever the thing you're measuring is, at which point you can think of it more of as a particle.
And some people have taken this to mean that it's the role of the observer to force the electron to act like a particle. If you watch a YouTube video about the double slit experiment, they might tell you something like that. But that's a complicated position to take, because it implies something special about this act of observing.
So I am not a fan of that idea. And I don't want to say that I can entirely disprove that idea. I don't think anyone can. And some smart people like Eugene Wigner and others over the course of the 20th century have taken that idea fairly seriously. But I think the idea that somehow consciousness interacts with the physical universe in such a way as to make the physical universe different, I think that's a pretty extreme hypothesis to consider. If you want to say that consciousness can collapse a wave function, then well, does it have to be a human? Does that have to be a smart human? Could a baby do it? Could an embryo do it? Could my dog do it? Could the fleas on my dog do it? Could an embryo of a flea on my dog do it?
Please get those fleas taken care of.
I don't even have a dog. I have cats. I'm more of a cat person.
So this interpretation of quantum mechanics, where observers force a wave function to collapse, it's not the only interpretation there is. There are different ones out there which don't require such a special role of the observer, but we'll get to those in a future episode. So back in our tour through quantum weirdness, we've now established wave-particle duality of light and other particles, but that implies something else, something we call the uncertainty principle.
So this is something put forth by Werner Heisenberg, again in the 1920s. He was one of the handful of people who were, there were a lot of people who contributed to quantum physics, but he was one of the biggest people, along with people like Schrodinger and Bohr and Dirac. And he deduced that for any wave function that was consistent with the Schrodinger equation, basically the right equation, that you could make these statements about the most you could know about a given object. So let's consider an electron, and let's say I had a physical situation where I knew very precisely where the electron was. The electron wave only occupied some very small region of space. Then you could deduce, according to Heisenberg, that you could know almost nothing about the velocity or momentum of that same electron. The more you know about the location, the less you can even in principle know about its velocity or momentum, and vice versa. So the more you know about its velocity, the less you can possibly say about its position. And the important thing is that Heisenberg wasn't making a statement about our ignorance, but was instead making a statement about the electron. It's not that the electron has well-defined position and momenta, but we can't know it. It's that the thing has many different positions and momenta all at once. The word that people use to describe this is superposition or quantum superposition. That electron is in a combination of different states, all with different locations and all with different speeds or momenta. And Heisenberg showed with his uncertainty relations, that the smaller the range of the locations that electron has in its superposition, the wider the range has to be for the distribution of its velocities and vice versa.
and it's not any two quantities which has this uncertainty relation. For example, we can't know both a particle's position in the x direction and its momentum in the x direction simultaneously, but we can know its x position and its y momentum, something in two different directions.
That's right. So the word we use, the technical word, is that the x momentum and the x position don't commute with each other. So you can't know both at the same time. But say the x position and the y position do commute. So in principle, one could know both of those pretty well at the same time. But then you wouldn't know the x momentum or the y momentum because they don't commute with the two positions. And
Right.
so
And
forth.
when we say commute, we literally mean like the normal math, like x times y equals y times x.
That's right. Yeah. The order you multiply them together gets you different answers, if you can believe that.
So there are certain quantities which commute with each other, in which case we can know them at the same time, and quantities like position and momentum in one direction, which we can never know exactly at the same time because they don't commute. And another example is energy and time.
Yeah. So it turns out that the Heisenberg uncertainty relation between position and momentum means exactly the same thing as a different uncertainty relation between the energy of an object and the time at which it has that energy. So what that means is if I tell you there's this object and it exists in this particular state at this very, very specific time, you can't really say anything about how much energy it has at that time. Or if I tell you I've done a measurement and I know very precisely how much energy this object has, I can't tell you with any precision at all when that measurement was done. So energy and time have the same sort of ambiguity built into their combination as position and momentum do.
And that has the consequence that if you have some small enough time, there's some chance that some energy is being created and destroyed in that time.
Yeah, I mean, if I tell you that that for some like picosecond or something, which is a very, very small amount of time, if in that amount of time you can work out from the uncertainty relationship how much ambiguity there is in the moment in the energy of something. So once you know that, it's completely consistent with the laws of quantum mechanics that for that brief period of time, something could just start to exist with that much energy, and then that picosecond later, it's gone. In fact, the vacuum of space and time that make up our universe, this is going on all the time. Particles are just popping into and out of existence everywhere all around us. That's just kind of the nature of the quantum nature of our universe.
So basically, uncertainty tells us that we can't know everything about a system at once. In other words, we can't know any system perfectly.
Yeah, and I would just want to emphasize it's not about what we know and don't know, about how things are. This is it's not an epistemological statement; it's an ontological statement. It's really saying something about how the universe is, and that things are in superpositions, things are not in pure states. This is different from the kinds of probabilities we study in classical physics. So if I flip a coin, I might not know whether it will come up heads or tails, but it's going to come up either heads or tails. If I have a quantum coin and it's in a superposition of heads and tails, before I look at it, it really is both in a head state and a tail state at the same time. It's in a superposition of heads and tails. With a classical coin, I flip it and I cover it up and I don't look yet. It's either heads or tails. I just don't know which. A quantum object is heads and tails at the same time, at least until I do the measurement.
And with that, we'll move to our last stop on this tour through quantum weirdness. I really do think we saved the best for last because we're now going to talk about something called entanglement. This might be the weirdest thing about quantum mechanics, but it was never actually taught in my undergrad level quantum classes.
I remember it being briefly mentioned in my second semester of quantum, but then in grad school, I took a whole year of quantum and a whole year of field theory, and it was never mentioned in any of that. So I take your point. It doesn't seem to be part of the typical curriculum.
And I definitely advocate for a curriculum change in this regard, but moving on, let's talk about what entanglement really is.
So the best example I know of is this the following. So picture some sort of radioactive atom, and when it decays, it makes two particles. We'll call them a positron and an electron. And because angular momentum is conserved, if the electron leaves spinning in a clockwise direction, the positron has to leave spinning in a counterclockwise direction, and vice versa. They have to be spinning in opposite directions as they move away in order to have equal and opposite amounts of momentum, or angular momentum, since the original atom didn't have any angular momentum. So, but let's say that happens and you don't do a measurement right away. So the universe is in a superposition of states in which the first particle is clockwise and the second one's counterclockwise, and the state in which the first one's counterclockwise and the second one's clockwise. And then those particles travel far away from each other. And despite being far away from each other, they're both in this superposition, and they are entangled with each other. It's impossible that you could measure both of them to be clockwise. Their fates are intertwined. Their reality is intertwined. If one's clockwise, you know the other one's counterclockwise, and vice versa. At this point, the two objects have wave functions that are entangled with each other.
So there's a kind of analogy out there that seems to dispel the weirdness in this, but we're going to show why it doesn't. Imagine you have a pair of gloves, a left-handed glove and a right-handed glove. Without looking, you put the two gloves in two different boxes, so you don't know which box has each glove. Then, I take one box to New York, and Dan takes the other one to Chicago. If I open my box in New York and see a right-handed glove, then I instantly know that Dan's box has a left-handed glove, without him ever opening the box. So at first glance, this looks like a classical example where my measurement of the glove instantaneously affects Dan's glove, in not a way that seems particularly weird. But really, this classical example does not get to the core of what quantum entanglement really means.
Even if you don't know which glove you have in your box, it's one or the other in classical physics. I'm going to emphasize the grammar here. It's or. It's left or right. In quantum physics, it's not. You're in a superposition. That is not a state of your ignorance. That is a statement about how nature is. So I take my box, which contains a superposition of left-handed and right-handed gloves. That means my box contains a left-handed glove and a right-handed glove, not or, and.
But it doesn't contain two gloves, to be clear.
It contains one glove in a superposition of left and right-handed states. Yes, exactly. And then you open the box, and at that point, it would appear that you transition from being in a superposition of left and right-handed states to one or the other. And you know that some very long distance away from you, where the other box is, it's just transitioned as well from being in a superposition of one or the other to whichever one isn't in your box. So it is different. It's weirder. Because of the superposition of these states and the fact that you could separate them through space and still have them their wave functions be entangled, means that by acting on one of them, by collapsing the wave function of one, you can collapse at a distance the wave function of the other, ensuring that you in the end wind up with a left-handed and right-handed glove, or vice versa.
And at first glance, this seems to create a paradox when you think about Einstein's theory of special relativity. Einstein said that nothing can travel faster than the speed of light. But if you have two entangled particles and bring them far enough away from each other, then they seem to be able to affect each other instantaneously. In other words, much faster than the speed of light.
Yes, so I think historians of science have a lot of problems with the way that we talk about this paradox. This is, by the way, it's called the Einstein-Podolsky-Rosen, or EPR paradox. And it stems from this paper that Einstein wrote in the mid-30s with Podolsky and Rosen, talking about this sort of phenomenon. And the way I first heard about this, and a lot of people first heard about this, is that Einstein thought this was a paradox, and then Niels Bohr wrote a rebuttal showing it's not a paradox, and Einstein was wrong and Bohr was right. I don't think that's fair. I mean, Bohr did write a rebuttal, and he tried to do that. But I'm not sure that Bohr really understood what Einstein was saying, and I don't think Einstein necessarily thought the same stuff that people say he thought. But it's kind of unclear what people thought and knew at different times. So I'll just say that I don't think it's a paradox in the way that people usually talk about it. In particular, even though it seems like something is traveling faster than the speed of light instantaneously when you collapse one wave function and then somewhere else a wave function collapses instantly, it turns out you can't use this phenomena to communicate or send information through space faster than the speed of light. And that's really what Einstein's theory of relativity says can't be done. It doesn't say that you can't have collapses of wave functions that extend across space or something like that. That's actually consistent with relativity. So it's not, I don't think there's anything about quantum entanglement that is fundamentally problematic from a perspective of relativity. Now, it may be a paradox in some sense of it just being super counterintuitive. And I mean, a lot of our paradoxes in physics aren't really paradoxes. They're just surprising. The twin paradox and special relativity is a good example, and things like this. So I would say that like there's nothing about the EPR paradox that should give you doubt that quantum physics works or is right. It doesn't show there's any problems with it. But it does illustrate just how weird some of the consequences of quantum physics are.
Another way to think about the resolution of this paradox is to think, okay, so you have your two entangled particles and one person holding each particle. But even if person A collapses her wave function and changes the wave function of person B's particle, person A can't actually tell person B what she collapsed his wave function to without communicating in the classical ways that obey the speed of light rule. So it's not actually like person A and person B can communicate instantaneously.
It maintains the less than speed of light restriction on any travel or communication. It's totally consistent with causality and logical self-consistency of space and time and all this stuff. If something could really travel faster than light, like you could really you built some device that could get information from point A to point B faster than light, that would be a big problem. Because if that were true, then you can look in some other frame of reference, it turns out, and you'd be sending information backwards through time. And once you can do that, you have yourself a time machine. And if you have a time machine, you can send a message back to somebody saying, you know, kill my grandfather before he meets my grandmother. And then my grandfather never meet. I'm never born. So I don't send the message back. So my grandmother and grandmother do meet. I am born. So I send the message back. And you know, logical self-consistency just falls apart. That's a real paradox. And that leaves me very confident you can't travel backwards in time. But quantum entanglement doesn't have any kind of problems like that. Not really.
Mm-hmm. So entanglement, super weird, but it doesn't necessarily violate any kind of laws of gravity, and it doesn't actually violate anything that we know is true.
Yeah, other than what we might have thought common sense said, but common sense is often wrong in modern physics.
This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.